Hello, I welcome you all to the 15th online lecture of the course Experimental Methods in Thermal Engineering. In our previous lecture, we had discussion on the measurement of static and dynamic contact angle. In this particular lecture, we will start with the measurement of another fluidic parameter which is particularly known as pressure. Okay. So pressure is identical to that of stress only. So if you see nothing but as we are having the definition of stress as force per unit area. So similarly, the pressure applied by the fluid or the force applied by the fluid on an unit area is something which is referred to as pressure. Okay, but there is a slight difference in between the pressure and stress. Stress is nothing but a second order tensor, whereas pressure is actually a scalar quantity. Okay, so why pressure is a scalar quantity? Let us try to see with the help of this small illustration. So in this particular example, what I have done, I have considered a two-dimensional planar surface. Okay, now in this surface, say particularly at this plane, if I have to define some stress, so I'll be writing sigma, and this plane is actually particularly nothing but our x plane. So first subscript will be referring to the plane on which we are defining this stress, and then we will be having some second subscript which will be referring to the direction in which this stress is acting. So you can see over here this stress vector is actually pointing in x direction, so I'll be writing over here sigma xx. So this type of stress is something which is known as normal stress because it is normal to the surface. Okay, so this is the surface and it is acting in a direction normal to the surface. Then we may have another type of situation where we are having some stress which is acting parallel to the surface. Okay, so this type of particular stress is something which is known as shear stress. So in this case, what will be happening? We will be having tau x because it is acting on x plane. However, the direction of this stress is nothing but y. So we will be having over here tau x y. Okay. However, if we talk about pressure on this fluid element, in case of pressure, what will be happening? The very first characteristic of the pressure is that it is of compressive nature. So it will be always acting on the fluid element and it will be actually towards the fluid element. So that's why we will be having something like this P as pressure over here. Okay, so this P is nothing but it is representing the pressure which is acting on this fluid element. Another characteristic of the pressure is that while it will be acting on a surface, its direction will be always normal to the surface. Okay, so it means it cannot act in any orientation with reference to the surface. It will be always having normal direction while it is actually acting on some particular surface. So there are two characteristics. One is that if you see practically pressure is having some magnitude also and it is having some direction also. So it means it satisfies the fundamental criteria which is required to define a tensor, but it is having some special characteristics, and the special characteristics is that it will be always of compressive nature. So one thing is that, and second is it will be always normal to the surface. So these two things, particularly these two special characteristics of this quantity pressure, these are actually uh, fixing the direction in which pressure should act. So because of that, we consider pressure as nothing but special type of tensor, and which shows the behavior of nothing but a scalar quantity. Okay, so that's why we call pressure as our scalar quantity. But in actual practice, it is nothing but it's a special type of tensor which is actually showing the characteristics identical to that of scalar only. Okay. Now, when if we see that if we are having some container, and inside this container if we are having certain amount of gas, so what will be happening? Inside this container we will be having large number of gas molecules. Okay, so these gas molecules will be having their molecular motions, and because of their molecular motions actually they will be interacting with the wall of the container. Okay, so while these molecules will be interacting with the walls of the container, as per the molecular kinetic theory, they will be developing some pressure on this surface. Okay, and that pressure is nothing but equal to, from the molecular kinetic theory, it is 1 by 3 nm V RMS square, where m is nothing but molecular mass, This N refers to the molecular density. So the meaning of this is nothing but number of molecules in unit volume. So that is N, and this VRMS refers to the root mean square velocity of the molecules. Okay. Then this VRMS is something which is a function of temperature field. Okay, so that's why it is nothing but equal to square root 3 kT by m, where this T is nothing but temperature in absolute scale. This K refers to the Boltzmann constant and m is molecular mass. Okay. Now we are having one important parameter which actually is used while we study the concept of continuum, and that particular parameter is referred to as mean free path, lambda. So this lambda is nothing but it is referred to as mean free path. So this mean free path, as per the definition, it is nothing but the average distance between the molecules, or whatever the distance molecules travel between the two successive collisions. Okay. So this mean free path is nothing but equal to square root 2 divided by 8 pi r square into n. So this is the definition or mathematical formulation for this mean free path. However, this mean free path is actually a strong function of the pressure and temperature of the system. So because of that, there is one relation which relates mean free path to temperature and pressure field, and it is like 2.27 into 10 to power minus 5 times T by T, where T represents the pressure in pascals and T represents temperature in Kelvin. Okay, and this will be giving the value of mean free path in nothing but SI units, so in meters. Okay, then we do now the measurement of pressure, but while we measure any of the physical parameter, what we do, we first specify some reference point for measuring that parameter. Okay, so for the pressure, what we are having some scale where we define the zero value of the absolute pressure, and this zero value of the absolute pressure is actually corresponding to the perfect vacuum situation. So if we are having a system where we are not having any fluid medium inside that system, corresponding to that we say that we are, because we will not be having any molecule, so we will not be having the molecular motions and we will not be having the development of pressure inside that. Okay, so that particular type of perfect vacuum situation actually corresponds to the zero value of the pressure. Okay, and if we are measuring the pressure of any system with reference to this zero absolute pressure, means with reference to the perfect vacuum physical situation, in that case what will be happening, whatever the value of pressure we will be finding, that will be nothing but in our absolute scale. Okay, then the value of our atmospheric pressure with reference to the zero absolute is something which is known as atmospheric pressure, and it is equal to 101.325 kilopascals. Okay, and then while we will be measuring the pressure now, we can take two different reference points. Okay, because this atmospheric pressure is also a standard value. Okay, though it will be depending upon the altitude of the location, but particularly at the sea level, its value will be always fixed. So that's why this can also be considered as parameter with reference to which we can measure the pressure of the system. Okay, so now from here you can see we are having nothing but the two reference point. One reference point is corresponding to zero absolute pressure and one is corresponding to the atmospheric pressure. Okay, so any pressure which is measured with reference to the zero value or with reference to the perfect vacuum, that pressure is actually something which is known as absolute pressure. For example, at this point, if my system is having this value, and if I am obtaining this value with reference to my zero, so I will be calling this pressure as nothing but my P absolute. Okay, ABS. And if I measure the same value of the pressure by considering reference at atmospheric pressure, so with reference to the atmospheric pressure, whatever the value of pressure I will be getting from here, that particular pressure is something which is known as actually gauge pressure. So it is written over here, positive gauge pressure. Okay, so that's why from here I can simply write one relation that absolute pressure is nothing but equal to atmospheric pressure plus the gauge pressure. Okay, so any pressure which is measured with reference to the atmospheric pressure, that is known as the gauge pressure. Okay, now one more thing we are having, if our value of pressure is greater than the atmospheric pressure, then we call that system as nothing but positive pressure system. And if our value of the pressure is less than atmospheric pressure, then we call our system as negative pressure system. Okay. Now, if we are having, say, this particular value of the pressure over here, so with reference, if we are measuring this value with reference to the zero absolute pressure, in that case, we will be finding over here that nothing but we have P, and this P is nothing but in absolute, and as our value of the pressure is actually less than the atmospheric pressure, so that's why we will be calling this situation as nothing but our vacuum pressure. So corresponding to this point, this pressure is nothing but absolute value of the pressure in vacuum. Okay, and if I have to now find out this particular value with reference to the atmospheric pressure, then with reference to atmospheric pressure, this will be something my negative value, because when we are measuring with reference to the atmospheric pressure, we will be having zero value set over here. So in gauge, 1 atmospheric, in gauge is nothing but equal to 0 gauge, and while we are going below the 0 value, so we will be having value of this pressure as negative value. So this is my gauge pressure, particularly in vacuum. Okay, so over here, if you have to relate this, I can simply write that my P absolute in vacuum is nothing but equal to, from here you can see this is my P atmospheric, so P ATM minus this value, so minus P gauge in vacuum. Okay, so over here this is the relationship between absolute, atmospheric and gauge pressure when we are having the positive pressure system, and this is the relationship between the absolute, atmospheric and gauge pressure when we are having the negative pressure system. Okay, so this is the actually basic fundamental thing which we should know while we are designing or developing or selecting the pressure measuring devices. Okay, because we may have pressure measuring system which is giving us the readings in absolute scale, and we may have the readings or instruments which are giving us the readings in gauge scale. Okay, so while we are selecting our system, we have to be actually very careful that what type of measurement device we should use in our system as per our requirements. Okay. Now, when to measure the static pressure or the steady value of the pressure, it is quite easy to measure, but we may have many times a situation that we are having some requirement of measuring the dynamic pressure. Okay, means the characteristics of our system actually is dynamic. Okay, so in that case, what will be happening? We have to determine the value of the pressure from our transducer, but obviously whatever the system we are employing for measurement, that system will be having its own characteristics. Okay, so obviously what will be happening, while we will be getting whatever the physically some phenomenon or some fluctuation is happening, whenever we will be getting its reflection in our transducer, there may be some amplification of the signal, and there may be some lag in between our physical occurrence of the pressure value and whenever it is reflected on the transducer. Okay, so that is something which is particularly depending upon the dynamic response of the pressure measurement device. So now let us try to see, let us first consider a general pressure measuring device, and for this particular type of device, let us try to see that what will be the dynamic response. Okay, so what I have done over here in this particular system, we are having a long thin tube which is having radius r and length l, and in the another side of this tube we are having actually one chamber, and the V is the volume of this chamber and P is actually the value of pressure which we are reading inside this particular chamber, and this chamber is then connected to some transducer which will be giving us the output value of the pressure. Okay, the other end of this tube is actually subjected to our system. So over here we are having our physical system where we want to measure the value of the pressure. So now over here what I have considered that within our system the value of the pressure is P naught, and at the output side we are getting the corresponding value as nothing but P. So now what we have to do, we have to now develop some relationship in between the P naught and P, and also we have to find out that if at at an instant we are getting the value of P naught, what will be the corresponding lag which will be actually reflected as a output in our transducer. Okay. So when we study this type of system, so there are certain assumptions, and particularly this type of system is actually considered identical to that of Helmholtz resonator in order to make it okay, Helmholtz resonator in order to find out its governing equations. Okay, so in case of Helmholtz resonator, what we are having a big cavity, and inside this large cavity we are having certain gaseous medium, so which will be having some pressure, say Pa, and some fixed volume as V. Okay, and then we will be having over here certain neck to that cavity, and inside this neck we will be taking some particular fluid element, and this fluid element will be actually subjected to some sort of oscillations, and because of these oscillations there will be a change of pressure within this cavity. Okay, so this type of particular device is something which is referred to as Helmholtz resonator. So over here also what we are having, this tube is nothing but reflecting this neck area, and this container over here is identical to that of this cavity. Okay, so what we are having now what we are doing, we are considering that we are going for measurement of the dynamic pressure. So obviously whatever this P naught we will be having, it will not be a constant value, rather this P naught will be a function of time. Okay, so obviously we may have fluctuations in this P naught, so it may have response something like this, which I have just shown over here. So this response is nothing but representing some sinusoidal oscillations in P naught as function of time. Okay, so what will be happening, these oscillations will be actually moving this fluid inside the tube. So because of this, this fluid will be actually moving either towards the left side or towards the right side, depending upon the nature of the pressure P naught. Okay, and because of these oscillations over here inside this chamber, we consider normally that we are having some compressible fluid, and because of what will be happening, because of that as particularly the fluid which is there inside the tube, it will be actually entering over here, so it will be reducing the volume over here, and because of this decrease of volume there will be increase of the pressure. Okay, and whatever the pressure change is actually happening inside this chamber, that pressure change will be then transferred or transmitted to the pressure transducer. Okay, so over here, what is basically considered, because we are considering over here that we are having nothing but a compressible fluid. Okay, so because of the compressible nature of the fluid, what we do, we consider this big chamber as nothing but identical to that of our spring. Okay, so this compressible chamber is nothing but becoming identical to that of our spring. Then what we are having this fluid mass which is there inside this tube, and that mass will be having some rightward and some leftward motion depending upon the value of the input pressure. Okay, so what will be happening, this fluid mass will be actually having some uniform motion. So considering the uniform motion and considering that our tube is actually very thin, we may consider this fluid mass as nothing but our lumped mass. Okay, so this fluid mass we can consider as identical to that of lumped mass, and while we are using the fluid over here, obviously that fluid will be real fluid, so that will be having certain viscosity. So because of the viscosity of the fluid, we will be having some damping also in between. Okay, so it means this entire dynamic system of the pressure transducer I can relate with the help of simple three components: mass M. So this whole fluid mass I have considered as a lump fluid mass. Then this big volume which is filled with the compressible fluid is considered as spring K, and because of the viscosity we will be having some damping also, so that C is our, say, damping coefficient. Okay, so now we know that if we are having this combination, so for this type of combination our equation is nothing but M x2 double dot, say if x2 is my output and x1 is input. Okay, plus C x2 dot plus k into x2 will be nothing but equal to k times of x1. Now if I divide both sides by m, so I'll be finding x2 double dot plus c by m x2 dot plus k by m x2 will be equal to k by m x1. Now we know from our earlier knowledge that omega n is nothing but equal to square root k by m, and my cc is equal to 2 into square root of k into m. Okay. So what will be happening if I try to relate in terms of these two parameters? So my x2 double dot plus c divided by m. Now I want to make in the denominator cc, so I will be multiplying by 2 into square root of km. If I am multiplying, I have to uh, uh, if I am multiplying in denominator, I have to multiply it in the numerator also. So 2 into square root of km x2 dot plus this k by m, I can write omega n square into x2 equal to omega n square into x1. Okay, so now this whole term is nothing but equal to cc. Okay, and this c by cc, we know that nothing but our damping ratio zeta. Zeta is equal to c by cc. Okay, so from here I can write x2 double dot plus c by cc. I can write it as 2 I am taking from here. Then c by cc I can write as zeta into, now this m, square root of m over here will be cancelling with this m, and we will be finally finding square root of k by m, which will be nothing but equal to omega n into x2 dot plus omega n square. X2 is nothing but equal to omega n square into x1. So from here you can clearly see we are getting nothing but our output. This is our output, and this is representing the damping term, and this is our spring force term. So over here with all these terms on the left hand side, we are having x2. X2 is nothing but our output, and that is represented with the in as a function of input parameter, and input parameter is over here as x1. Okay, so now because our this system whatever we have considered over here, it is also identical to that of nothing but a spring mass system under some set of assumptions. So because of that, what I can do, whatever this equation I have written over here, I can write, and I can write a similar equation for this type of system also by considering the analogy between the two systems. Okay, so while we will be writing the equation, particularly we are having output parameter as nothing but our P, and this P naught is an input parameter. Okay, because whatever the pressure we have to measure, that is acting as an input on our transducer, and whatever the output we are getting from the transducer, that is something, that pressure change inside this chamber, because that is something which is actually being then further transferred to our transducer. Okay, so by considering this analogy, I can write that in place of x2 double dot, I can write d square p by dt square plus 2 zeta omega n into dp by dt, okay, plus omega n square into p, and that will be equal to nothing but omega n square into p naught of t. Okay, so this is our main governing equation for this type of function. Now particularly for this fluidic system, what will be the value of omega n and zeta? Let us try to see. Okay, so these values, particularly the value of omega n, we can find with the help of Helmholtz and resonator. So particularly for Helmholtz resonator, what we do, we, as I have told you, we consider a cavity and then we consider a neck. Inside this we are having Pa as the pressure and say V as the volume. Okay, and particularly what will be happening, I am now considering that this neck is having say cross sectional area A, L is the length of the neck. Okay, so and rho is say density of the gas which we are having over here. Now what we will be doing, we will be considering another situation where whatever the fluid was there inside this neck, that fluid has been displaced through say very small distance x. Okay, so we have displaced this fluid with the value of small displacement x. So because of that displacement of the fluid, what has happened, there is some change in volume of the cavity. So because of the decrease in volume of the cavity, there will be some increase of pressure. Say the pressure has increased by amount P. Okay. So now over here, if you have to do the analysis, the very first thing is that particularly the mass of this fluid element I can determine as rho is its density and A is surface area, A is cross-sectional area and L is length. So mass of the fluid element will be equal to rho A into L, okay, and whatever the force this fluid element will be actually supplying on the system, that force will be particularly because of this x displacement, that force will be equal to small p into A, where A is nothing but our cross-sectional area. Okay, so now we can consider that whatever this fluid element we are having, this fluid element has displaced through displacement x. Okay, so if we try to write down the governing equation for this, I can simply write F is equal to mass into acceleration. From here I can write that my force is nothing but pressure into area, and mass is nothing but equal to rho A into L, and acceleration I can write as x double dot. Okay, so from this what will be happening, A will be cancelling over here, and I will be finally finding that my x double dot is nothing but equal to P divided by rho into L. Okay, now let us try to find out the value of this P in terms of the known pressure PA and the volume of this cavity. So what we can do, so if you see over here what is basically happening, this fluid element has displaced in downward direction. Because of that, the volume of the cavity has decreased, and that volume decrease has actually resulted in increase of the pressure. Okay, so if this phenomenon takes place quasi-statically, in that case what will be happening, we can simply relate the increase of pressure with the decrease of volume by considering that our temperature is constant. Okay, but over here what will be happening, because we are having some dynamic response, so obviously the phenomenon will be very fast. Okay, so considering the phenomenon as rapid, this displacement will be happening in very small fraction of time, so we cannot consider it as an isothermal or quasi-static process. So we have to consider over here that this displacement of the fluid element will also result in change in temperature of the gas, whatever we are having inside this cavity. Okay, so now one condition is that though we have considered that we are having certain change of the temperature, so obviously because of this change of the temperature, what will be happening, this cavity fluid will try to transfer the heat to the surroundings. Okay, but at the same point of time we are considering that our phenomenon is very rapid, so phenomenon will be so rapid that it will not be falling into the time scale required for the heat transfer. So because of that we can take the assumption of adiabatic compression of the gas inside the cavity. Okay, so what we are doing now, considering the rapid nature of the physical phenomenon, because we are particularly talking about the dynamic behavior of the system. So considering the rapid oscillations of the fluid element, we are considering that our compression process will be adiabatic because its time scale will be so fast that it will not allow sufficient time for the heat transfer to take place. Okay, so now we know from our knowledge of thermodynamics, for adiabatic systems PV power gamma is equal to constant. Now if I take differential, I can write dP into V power gamma plus gamma times V gamma minus 1 into dV into P will be equal to 0. So from here I can simply write that my dP divided by P is nothing but equal to minus gamma times V power gamma minus 1 into dV divided by V power gamma. So which is finally becoming identical to that of minus gamma times dV divided by V. Okay, so from here you can see that our dP by P is nothing but equal to, I can write as minus gamma dV by V. Okay, so now for our actual system, dP is nothing but PA plus P minus PA. Okay, so I can simply write small p as my dP and divided by our original pressure is nothing but equal to PA. So P by PA is equal to minus gamma into change in volume. So how much is the change in volume? The change in volume is nothing but equal to because of the x displacement over here. Okay, so we are having area as A and x represents the displacement. So A into x, whatever this lump mass from the neck has displaced into the cavity, by that amount we will be having change in volume of the cavity. So minus gamma A into x divided by original volume of the cavity as V. So from here I can simply write that my P is nothing but equal to minus gamma AX into PA divided by V. So so let me write over here x double dot equal to, instead of, so 1 by rho L I'll be writing as it is. Okay, and instead of P now I can write minus gamma PA into minus gamma PA into A divided by V. Okay, so and multiplied by x. So this is now my x double dot. Okay, now we also know that our speed of sound c is nothing but equal to square root of gamma into RT. Now considering the ideal nature of the gas, I can write that PV equal to RT, or V specific volume I can write nothing but 1 by rho. So I can write P by rho is equal to RT. Okay, so from here you can see we are having PA divided by rho into gamma. So this PA by rho into gamma I can write nothing but as my speed of sound in that particular fluid medium whatever we have considered. So from here what we will be finding that x double dot is nothing but equal to minus gamma, and instead of PA by instead of minus gamma PA by rho I can write minus c square. Minus sign is also gone. Okay, no, minus sign we will be having over here. So minus sign is, we are having only gamma into PA by rho is gone. Okay, so that has become nothing but equal to c square. So over here I can write x double dot equal to minus c square into A divided by L into V into x. Okay, so this is my now the final equation. Now, if you see this particular equation, in this particular equation, what we are finally getting that our x double dash is nothing but equal to minus of omega square into x. Okay, so that is something which is the equation of a simple harmonic motion. So this equation is particularly becoming, so over here, whatever the equation we have got, this equation is nothing but becoming identical to that of x double dot equal to minus omega square into x. Okay, so it means that whatever the oscillations of this fluid element we will be having, these oscillations will be having nothing but simple harmonic motion. Why simple harmonic motion? Because first this fluid element will be actually moving in downward direction. So because of that there will be increase of pressure. Now this increase of pressure will actually try to move it in upward direction, and once again then after reaching the maxima, when pressure will be decreasing over here, it will move down, and then this type of actually top and down oscillations will keep on happening. Okay, so it means the nature of these oscillations inside the Helmholtz resonator are nothing but of simple harmonic type. Okay, so if I make the analogy of this our actual equation with reference to the nature of the simple harmonic motion, where x double dot is nothing but equal to minus omega n square into x, I can simply write that omega n square will be equal to c square into A divided by LV. Okay, and from here if I consider my omega n is nothing but equal to 2 pi fn, where f is our natural frequency, so I can write fn as nothing but c divided by 2 pi, c divided by 2 pi into square root of A divided by LV. Okay, so this is something which is nothing but the formulation of omega n, whatever we are using over here in this equation. Okay, and now if we further go through this analysis, finally we will be finding the value of zeta as nothing but 2 mu times divided by rho into AL. Okay, So this will be the value of zeta. If we further do the analysis and try to relate the value of damping ratio, so from here we will be finding the from our analysis we will be finding the ratio damping ratio as 2 mu times divided by rho al. Okay, so this is clear to all. So this is nothing but our main governing equations and what are the different parameters in our governing equation. Okay, now depending upon the input to this particular system, we will be having the response obtained from the system. Okay, so over here we will be giving input parameter as nothing but P naught times T. Okay, so now in this next slide, what I have done, I am not showing you the detailed solution, but what we are doing, we are considering the dynamic response of the pressure, particularly for our simple harmonic input. So now I am considering that my input function P naught T is nothing but equal to, say, P A is my amplitude, or I can simply write P naught as my amplitude, P naught times sine omega t. Okay, so we are having the simple harmonic nature of the pressure which is acting on, and corresponding to that, if we take the ratio of the amplitudes P divided by P naught, where P naught refers to the input amplitude and P refers to the output amplitude, we will be having 1 divided by so we are having this bracket which represents the square root of the entire quantity. So 1 minus omega by omega n square whole square outside plus 4h square omega by omega n square, where this h is nothing but used here as an replacement for symbol zeta. Okay, so where zeta represents our nothing but damping ratio. Okay, which is equal to C divided by Cc. Okay, so while we will be further analyzing our system, and if we try to find out the value of natural frequency in terms of our radius and length of the pipe, we will be finding natural frequency as 3 pi r square c square divided by 4 lb square root, and h will be equal to 2 mu divided by rho c r cube into square root of 3 lb by pi, and this pi represents nothing but phase lag in between our input and output, so that will be equal to tan inverse minus 2h omega by omega n divided by 1 minus omega by omega n whole square. So this omega over here refers to the frequency of our input function, so the rate at which actually pressure oscillations are happening, and this omega n refers to the natural frequency of our mechanical arrangement which has been used for developing the transducer. Okay, and if we have to find out the speed of sound particularly in air, so for that one equation is given 20.04 t to power 1 by 2. Here this actually speed of sound is given as a function of temperature. Okay, now what can happen, we may have a situation where particularly this term will be of a very small magnitude in comparison to this term. So for that type of system, what will be happening, we will be having this portion over here, this will be neglected, and we will be having, so when this is happening when we are having the ratio of omega by omega n as very small. Okay, so in that case particularly this portion over here will be negligible, and because of that we will be finally finding the value as 1 plus 4h square into omega by omega n square 1 by 2, and natural frequency for this type of system now over here will be becoming pi r square c square divided by volume into with length what we are doing. So if you see my previous formulation, there what we were having frequency was nothing but c by 2 pi square root a by lv. Okay, so now in place of l, what we are doing, we are considering some more length portion. Okay, so we are actually adding some length. So this particular portion is actually added over here in order to account for the effects of compressibility. And moreover, when actually fluid enters inside this tube, there will be some entrance effect, because of which actually we will not be having always the uniform fluid motion which we have actually considered earlier. Okay, particularly near the inlets. So what we have to do, we have to use some corrected length or some effective length while we are determining the natural frequency. Okay, so this additional portion over here is actually representing that correction which has been added into our system. Okay, so from this particular equation you can see that we will not be having immediately the reflection of change in pressure in the system on our transducer. Rather, we will be having certain phase lag in between our input function and output whenever we are obtaining from the transducer. Okay, so in this particular point, you can clearly see that till this point we have only studied the mechanical portion of the transducer, and we have considered that because of the mechanical portion of the transducer, we are having certain phase lag. Okay. However, after this, what we will be having, we will be having some electrical system also, which will be actually connecting or transferring this signal into our electrical signal. So we may have certain characteristics of that electrical system also, which may once again lead to more lag and complexities in our system. Okay, we are only over here talking about simply the mechanical arrangement which has been actually used to fabricate the transducer. Okay, then so what I have done, I have just given you the overall idea of the dynamic pressure measurement. So it means that when we are doing the dynamic pressure measurements, we have to always consider the phase lag and rise time of the transducer. Okay, and while we are selecting a transducer for our practical applications, the rise time of the transducer should be less in comparison to the physical time scale of the phenomenon. Okay, because if our physical time scale of the phenomenon is actually less in comparison to the rise time, then obviously we will not be able to acquire the correct values of the pressure. Moreover, fluctuations in our physical system will be happening at the faster pace, whether pressure response of the pressure transducer will be giving us some value of pressure which will be actually not accounting for the all the fluctuations which are happening in our physical system. Okay, so now this is only for your understanding that while we are selecting the pressure transducers, then we have to take care of rise time and phase lag as the important parameters in order to consider our pressure transducer for the dynamic measurement applications. Okay, now let us try to see few basic measurement methods. So the one of the fundamental mechanical measurement method is called as basic manometry. So over here what we are having some U-tube type arrangement. So we are having some tube over here, and inside this tube we have filled some fluid, and this particular fluid is actually known as manometric fluid. Okay, so the fluid which we are using over here, we call it as manometric fluid. Then over here we are having some chamber inside which we are having some gas, and because of that gas some pressure will be acting over here. So one end of this manometer is actually connected to the gas chamber and other end is actually open to the atmosphere. Okay, so what I can do, if I just try to find out the balance of the pressure. So we always know from our knowledge of basic fluid mechanics that pressure varies with the height. So if I have to consider over here the variation of pressure, I can write, if P is the pressure at this point, I can write that P is nothing but equal to, and say rho m is the density of this manometric fluid. So I can write P is nothing but equal to rho m into G into H. Okay, so now we are balancing the pressure with reference to this particular point. Okay, so what will be happening over here? So if I consider this outside pressure as 0, if I don't include it over here, so whatever the value of pressure I will be getting from this equation, that will be nothing but in gauge. If I have to find out the value of pressure in absolute scale, then obviously my P absolute will be equal to rho m G into H plus P atmospheric. Okay, because P atmospheric pressure is also acting on this manometric fluid, and this P absolute is nothing but absolute pressure of the gas chamber. So whatever this gas we are having over here. Okay, so this is the basic mechanical measurement device which is known as a U-tube manometer. Okay, now in this particular type of U-tube manometer we may have another situation that we will be having the pressure signal which will be coming something like this, and we are considering that say A1 and A2 are the areas of these two different tubes. So we can consider the different area also, or we can consider the same area also. Majority of the times we will be considering the area as same, because then we will be having the same amount of displacement of the fluid in both the directions, in both the sides of the tube. Okay, so over here if we consider that P is the pressure and P atmospheric is acting over here, and this fluid is nothing but our, say, rho F, and this is our manometric fluid rho M, and over here also we will be considering that our rho F is the fluid which is actually flowing inside this tube. Okay, so in this particular thing, if you want to balance the pressure, where you are taking reference as this point, and we are balancing the pressure particularly between these 2 points. So I can say that my P plus, over here we are having density of the fluid as rho F. So rho F G into H, that will be equal to, this side we are having manometric fluid, so rho M G into H, plus we are having PA as the atmospheric pressure. Okay, so from here I can simply write my P minus PA is nothing but equal to rho M minus rho F into G times H. Okay, so this is my pressure when we are pressure difference between these 2 points. Okay, so what we do, we are considering that over here, whatever the height of the liquid column we are having, there we are having the density of the fluid as same. Okay, so whatever the pressure head we will be having over here, that will be actually cancelling out with this pressure head. Okay, so it means we are considering that this is the point about which we are actually balancing our pressure. Then we may have some more variants of the manometer, where we consider that we are having well type manometer. So in well type manometer, what we are having a big tank like structure, and which is, this tank is actually connected to some scale over here. Okay, so in this particular arrangement, if you want to measure the pressure once again about this point, I can write P minus PA equal to nothing but my rho M into G into H. Okay, so this is the simple balance of the pressure I can do. But over here what will be happening, while we will be having certain change of the height. So over here, say if my change of height is happening by amount h dash, corresponding to this h dash amount, we will be having some another change of height over here, because now we are having the area ratio is not uniform, so we will be having certain different value of change of height over here. So because of that, what will be happening, whenever we are considering our height over here, we have to consider the effect of the area ratio. Okay, so effect of this area ratio will also be coming into picture. But in the practical scenarios, while we employ this well type of manometers, what we do normally, first we calibrate these manometers. So what we do first we calibrate these manometers with reference to atmospheric pressure. Okay, so what we do, when we connect this pipe to atmospheric pressure only, at that time we fill certain amount of this manometric fluid inside, and we fill this manometric fluid in such a fashion so that corresponding to its neutral value, we are getting zero reading from this. Okay, so we are getting zero reading, and when we will be subjecting now this to some pressure which is other than the atmospheric pressure, now because of that, what will be happening, when here we will be having more fluid pressure, we will be having the displacement of the manometric fluid. So because of that displacement of the manometric fluid, obviously what will be happening, in this particular side we will be able to measure the height. Okay, so what we do, because we have calibrated it for atmospheric pressure, and we have filled the manometric fluid till its zero value, then whatever the change of height is happening inside the tube only, that only we consider for finding out the value of pressure. Okay, but while this type of manometers are calibrated, generally we don't take over here the linear scale, whereas the scale of this type of manometer is actually graduated in order to account for the effect of the area. Okay, so we are having over here graduated scale, and that graduated scale particularly accounts for the effect of this area ratio. Okay, so this point you have to clearly understand, that while we have to employ the well type manometer, always before taking the reading, first we have to calibrate that with reference to atmospheric pressure. With reference to atmospheric pressure, that should show the zero on its scale. Okay, scale particularly on the tube side. And after that, because over here we are having a very large area, so it is very difficult to measure the change of height, because this change of height will be very small. Okay, so already while we design the device, instead of considering the linear scale over here, the nature of the scale will be linear only, but there will be some amplification factor considered over here in order to account for the change of level because of this area ratio A1 by A2. Okay, so this type of scale over here is referred to as graduated scale, and the main purpose of this is that we need not to find out the change of this height, rather the reading on the scale itself will be actually giving us the final measure of the pressure. Okay, now if we have to go for more accurate measurements of the pressure, then particularly in this well type of arrangement, we are having one more particular device which we call as nothing but inclined manometer. So in case of inclined manometer, over here we are having the manometric fluid, and this side is actually connected to atmosphere, and in this particular thing we will be actually connecting to our system. Okay, so over here what will be happening, we will be having actually scale marked over here on this particular angle. Okay, so say if for any given value we are finding the length over here as L. Okay, but what we have to do, while we actually find out the value of the pressure, we have to measure the length of the fluid or height of the fluid along the gravitational axis only, because this pressure is actually being developed because of the acceleration due to gravity. Okay, so what we will be doing, say if this theta represents the angle of inclination of the manometer, and along the gravitational side, if we consider that h is my actual height, so I can relate from here that h divided by L is nothing but equal to sine theta, and h will be equal to nothing but yes, h by L is equal to sine theta, and h will be nothing but equal to L times of sine theta. Okay, so over here you can see that the value of h will be actually smaller in comparison to the value of the L whatever we are obtaining from here. Okay, so this simply I'll try to relate with the sensitivity of the manometer. So what will be the sensitivity of the manometer? Sensitivity of any device is nothing but it represents the whatever the output we are obtaining corresponding to the unit change of the input. Okay, so that will be nothing but h divided by delta p, because delta p is our input and h is our output. Okay, so this h divided by this delta p will be equal to rho m manometric fluid minus rho of our fluid under observation g into h. So this h will be cancelling out, and finally we will be finding our sensitivity as nothing but 1 divided by rho manometric fluid into g, if we consider that our density of the manometric fluid is very large in comparison to density of the fluid which is under observation. Okay, so from here you can see that sensitivity of the manometer is nothing but a function of the manometric fluid. So for example, if we have to measure the pressure for very small range of pressure or for very small changes in the pressure value, in that case we will be considering the light fluid as our manometric fluid, and if we are having very large range of the pressure measurement, in that case what will be happening, the large change of pressure with lighter density may require significantly large amount of height, which may become difficult to handle for our device in the practical scenarios. Okay, so for the large pressure values we can go for the heavy manometric fluids. Okay, and particularly the purpose of inclination is to make the amplification of this scale so that we can accurately read the scale for the small fluctuations in pressure. So particularly this inclined manometer is also considered when we are having actually variations in the pressure as small. Okay, because this is more sensitive in comparison to the conventional U-tube design when we are having variation along the gravitational field only. Okay. Then one variant of the manometer is particularly known as barometer. So in this particular variant, what we do, we take a container, and inside this container actually we take our manometric fluid. For example, over here mercury is taken, and then we take an inverted tube inside, we put it inside our container. Okay, so now what will be happening over here, inside over here at this surface we will be having atmospheric pressure which will be acting, and particularly in this zone of the tube which is actually vacant, here we will be having vacuum, or at max we may have vapors of our manometric fluid. Okay, so we may have vapor phase of mercury. Okay, so particularly corresponding to the atmospheric pressure, if we take our temperature condition as 15 degrees Celsius, so particularly at 15 degrees Celsius, the vapor pressure of the mercury is very small in comparison to the atmospheric pressure. So while we will be considering this liquid column, so we are having this liquid column over here between points B and C, and in this liquid column, the weight of the liquid column is rho g h into A, where this A is nothing but the cross-sectional area of the tube. So what we are having over at this point, we will be having the vapor pressure of the mercury which will be acting over here, and I am saying that at 15 degrees Celsius the vapor pressure of this mercury is very small in comparison to the atmospheric pressure. So because of that I can consider it nearly equal to 0, and from here we are having the atmospheric pressure which is actually supporting this liquid column. Okay, so because of that what will be happening, we will be having the balance between this pressure over here with this one. So simply I can find from here that my P atmospheric is equal to rho g into h. Okay. Now irrespective of the cross-sectional area of the tube, if you take the tubes of different area, we will be having always the same value of the height over here. Okay. Because while we are balancing the weight and the force because of the pressure, area term will be cancelling. So we will be finding that pressure is nothing but function of height irrespective of the area of the tube. Okay. The only thing we have to consider that while we are selecting the diameter of the tube, it should not be as small so that our surface tension effects are becoming significant. This we have already seen that surface tension is a parameter which depends upon the curvature, and if our radius of the tube is very small, at that time our value of curvature will become large and surface tension forces will be becoming prominent, and these will also additionally act over the, or will try to counter our gravitational effects. Okay, so that's why while we select our tube for the manometric applications, we have to consider the tube diameter in such a fashion so that our effects of this one surface tension are actually negligible. Okay, then normally what will be happening at the sea level, if we measure the value of atmospheric pressure, we will be finding height as nothing but 760 mm of mercury. Okay, however, when our altitude changes, with change of altitude there is change of the pressure value. Okay, so for that we are having one equation which represents this P naught as considering P naught as a sea level pressure, which is nothing but equal to 760 mm of mercury. So with increase of altitude, what will be happening? One P will be related with P naught as P equal to P naught times 1 minus B into Z by T naught to power 5.26, where this Z actually refers to the height and this temperature is nothing but in Kelvin, and value of B is equal to 0.0065 Kelvin per meter. Okay, so depending upon the condition of the temperature and depending upon the height or altitude, we will be having actually value of pressure, and particularly the pressure will be actually decreasing with increase of the height. Okay. Then we are having one more arrangement for measuring the pressure, and this particular arrangement is actually known as dead weight tester, and this dead weight tester is actually it may be employed for measurement of the pressure. However, it is a fundamental standard which is actually considered for calibration of our pressure measurement devices. Okay, so it is used as calibration standard for measurement of our for calibrating our standard pressure measurement devices. Okay, so in this device what we are having a chamber, and this chamber is particularly filled with some oil. Then we are having a piston over here. So this piston is actually very tightly fitted with the cylinder. Then we are having one additional plunger over here, and then we are having a pressure gauge over here which can be connected with the valve. Okay, and over this piston we can add some weight, and that weight will be actually giving us the pressure over this fluid medium. Okay. So what basically happens, while we will be keep on increasing the weight, then obviously the pressure within this fluid will be increasing, and then the device which we want to calibrate, we will be connecting over here with this valve, and then we will be opening the valve. So while we will be opening the valve, whatever the fluid pressure we are getting over here, that will be transferred to the uh, this pressure gauge which we want to calibrate. So whatever the value of pressure we will be getting from this, that can be related with the amount of weight we have supplied multiplied by the area of the piston. So effective area of the piston. So this piston is actually very tightly fitted to the uh, cylinder. So though this particular device is actually having very less chances of uncertainties and error, the only uncertainty or error will be coming because of the static coefficient of friction in between the cylinder and the piston valve. So in between the cylinder and the piston valve, there will be some friction. So because of that friction only, small errors may come, and in order to avoid these errors, generally what is done, this piston is actually subjected to some sort of rotation. Okay, why rotation? Because when these will be having some motion, there will be some thin film of the uh, liquid over here which will be rising, and always the value of this kinetic friction will be less in comparison to the static friction, so that will be actually leading to lesser errors in this particular type of system. Okay, and the sole purpose of this plunger is in order to account for the compressibility effects, and particularly when we have to calibrate some device at very high value of the pressure. So in that case, what will be happening, this high value of pressure may produce some sort of compressibility inside this oil. So because of the compressibility of the oil, there may be decrease in the oil volume. So in order to compensate for that, we can actually move this plunger in inward direction, and this plunger will be actually then accounting for the effect of the compressibility. Okay. So this particular device is actually standard for calibration of our different pressure measuring devices. Okay, so now what I will do, I will stop at this point, and then we will continue our further discussion in our next lecture.